Good afternoon, everyone. Welcome to the final session of day 2 here at ETE 2021. Glad we got our technical difficulties solved. I'm Matt Swartley with Chariot Solutions. I'm here to introduce you to John Merlino, who is a committer as well as the PMC chair for the Apache Druid project. John is going to speak with us today about the challenges of choosing a large-scale data analysis system. So with that, take it away.
All right, hey everybody. Sorry for the scheduling snafu. I greatly apologize, but thank you for hanging around anyway. So today I'm going to talk about a topic that's near and dear to my heart. It's thinking about different sorts of analytical solutions on a temperature spectrum and how they relate to each other. Why is nothing perfect? Can we have it all this exciting stuff. First off, let me talk about a little bit who I am. I am Gian Merlino. I'm a committer and PMC chair at the Apache Druid project. Apache Druid is a real-time analytical database. And I am a co-founder at Imply, a company that is based around Apache Druid. And we are hiring for this kind of stuff. So if you're interested and if it seems cool, then come talk to me afterwards. So today, what I want to talk about is first off, a data temperature spectrum from cold to hot and what that means and what that suggests for the kind of systems you're going to be interested in analytically. We're going to go on a tour of sort of the past, present, and future of the data world as it relates to analytics and this temperature spectrum. We're going to meet Apache Druid, the project that I work on. And then finally, we'll talk a little bit about the future. Can we have it all? How useful would the spectrum be going forwards? So without further ado, things that you hopefully care about. So if you care about these things, then I think this way of thinking is going to be useful to you. This hot versus cold way of thinking, what you care about if you are on the spectrum is on the top here. We have these hot use cases. This is there's a bowl of hot Cheetos and Takis and lime and cilantro and all that nice stuff. Very hot, very exciting. What does that mean? It means we want sub-second queries. We're trying to evoke freshness, fastness, high concurrency, and highly interactive. And so these are data-driven applications. These are use cases where lots of people access the same data set at the same time, that kind of thing. Online analytics is what we would call it. And then on the other side of the spectrum, we have cold use cases. Cold use cases where there is, here we have a picture of a warehouse full of government cheese. And it's no coincidence, this is a warehouse. A lot of times the data warehouse is where you put your colder use cases. In situations where slow queries are okay, less fresh data is okay, you're going to have relatively low concurrency, and you're going to be focusing mostly on reporting and planning. So, okay. What do I mean by, I want to take a little bit of a detour to talk about online analytics. I said, hot use cases mean online analytics. This is a video screenshots, moving screenshots of Imply Pivot, an application we work on at Imply. That is really, I think, a good exemplar of the kind of application that's a hot analytical experience. And these things have to be videos, I think, instead of screenshots, because screenshots don't really do the experience justice. The experience is meant to be very fluid, very interactive. We really want to make it so each individual query is very quick. And so you can sort of explore through your data, have a conversation with the data, not just be running individual queries. And so this is a example of the kind of experience I'm talking about when I talk about hot analytics. Use cases for that. So what are the use cases for OLAP analytics? The big two are exploration and monitoring. And they come together to make real-time OLAP. So exploration tends to be something that is mostly historical, although you can do some on real-time data, but a lot of time you're exploring historical data. You're looking for trends, you're looking to root cause things that have happened in the past. You're looking for little slices of the data that are interesting. You're looking to explain trends is a big one. You might see the top line metric change, and you want to understand why did it change. And that requires a bit of exploration to understand why. On the other hand, we have monitoring. Monitoring is a very real-time use case. And what I mean by that is you're not really monitoring things that happened 3 days ago, you're monitoring things that are happening right now. So that might be monitoring a rollout of a new product or that kind of thing. Monitoring observability of a live system. And these two use cases come together to form these hot analytical workloads. There's situations where we want to do a lot of slice and dice on what's happening right now, but also on what's happened in the past. Where are these useful? These are useful in a lot of different kinds of applications. I'm not going to talk about any one of these in great detail, but things like data-driven applications, risk and fraud analysis, digital advertising, click streams, observability, network performance. These are situations where people tend to deploy applications where hot speeds are very useful, where you want to deploy an application that's going to be used by a big team of people highly concurrently, that kind of thing. So this begs the question, why tolerate cold data at all? If the hot stuff is so great, if it's so fast, if it's so online, if we can support high concurrency, what's the point of tolerating cold data? Why do we even do it? And there's two reasons. One reason is that in today's market, the technologies that focus on cold data tend to be a bit more powerful in terms of what kinds of queries it can do. And they also tend to be lower cost if you are accessing the data very infrequently. So these technologies tend to focus on spinning up compute on demand when you need it, and then spinning down the compute when you don't need it. And this sort of on-demand or very rapid elasticity lowers costs for infrequently accessed data. On the flip side, the systems today that are built for these hot analytical use cases tend not to focus as much on being able to do every possible query you can throw at it. And also they tend not to focus as much on spot elasticity. They tend to focus more on being really, really good and very good price performance for frequently accessed data. The idea being that if you are accessing data 24/7, then these systems are going to be faster and cheaper than the cold systems. And so there's sort of economic benefits at both ends of the spectrum. And I'll get into that. I'll get into why that is in a bit and how we think about that. But I think that the point I want to make on this, slide, and the point I'd hope you take away from this section is that it does help to think about do you have a hot use case, or do you have a cold use case, and using a system that is built for that kind of use case. Okay, so now I want to talk a section called Strolling down memory lane, and we're going to talk a little bit about the history of analytical systems, where we started, how we got to today, and this will help us think about categorizing them into what they're good at. Okay, so in the beginning, there was the relational database, one size fits all. So you have the same database used for your transaction store as you are using for your analytics. And this is great. It's very simple. You have a single database used for everything. The only issue is that it doesn't scale very well. And one of the biggest problems when you're running reports on the same system as you are using for actually run your business, to actually run your transactions, then that can cause cross chatter between them. It can cause you can take your e-commerce site down by running big analytical queries. It's not great. It's not a great idea. So the next thing that folks developed out there in the world is data warehouses. So the concept of a data warehouse is twofold. One is we are going to, by separating the warehouse from the transactional store, we can do two things. One is we can eliminate issues where the warehouse is, or where analytical queries are going to impact the performance of the transactional store. And the other thing we can do is we can optimize the warehouse for analytical queries. And so at this point where these things separate is when people start thinking, oh, wow, it'd be great to, I use a row store for my transactional store, but I want to use a column store for my warehouse. And each one is going to be good at different kinds of things. So this is cool. And the next thing that people do is they realize that warehouses are are getting overloaded. So what happens is the business has a big old data warehouse. People are doing all kinds of stuff with it. These queries are getting slower and slower, bogging down more and more because we're doing all kinds of things. We're doing reports, we're doing dashboards, we're doing ad hoc queries, we're doing everything under the sun that's analytical. And so what develops to try to address that problem is this concept of an OLAP database. And an OLAP database is something that sits to the side of your data warehouse and is this is sort of the first concept of hot analytics, and this is pre-big data. This is still single server, but it's the idea is that you load a copy of certain tables, maybe summarized, into your OLAP database, and then you power slice and dice use cases, fast use cases on that, and you use the warehouse for everything else. You use the warehouse for ad hoc reports, ad hoc querying, that kind of stuff. Things that aren't your UI-driven slice and dice applications. And this is a setup that, in large part, has been recreated today in the big data world. I'll talk about how that works. But before then, we need to talk about the big data world and how it changed everything. So at some point in the 2000s, big data descends upon all of us and changes everything. And so nothing is one machine anymore. You used to have, one transactional store, one data warehouse, and one OLAP database. Nothing is one machine anymore. Everything is scaled out. You're going to have potentially sharded transactional stores. This is the era when people are talking about how, wow, it's great if I don't just want to have one MySQL database. I want to have 1,000 MySQL databases sharded by customer ID. So you're going to have sharded transactional stores. You're going to be loading data from the store that runs your business into a data lake, which is pure storage. And then you are going to be using a scale out query engine in order to query it. And these query engines are going to be something like Hive or Presto or Spark or something like that. One of the Hadoop MapReduce being one of the first ones, and then newer, better ones that came out over time. So this is the big data era. It looks a little bit like a super scaled out version of the second picture from the pre-big data era. So there's this sort of lake plus query engine is doing the job of the warehouse. And then these scaled out transactional stores are replacing single transactional stores. Everything old is new again. That is how technology works. So of course, in the big data world, folks started to create serving databases. And these serving databases are like the big data equivalent of these old-timey OLAP databases. And serving databases store an optimized copy of what's in the data lake. They may also be able to load directly from a streaming source like Kafka, which is nice, bypassing the data lake completely. And the idea is that it's the same as what you would use the old-timey OLAP databases for. You would use them to serve slice and dice use cases, these hot use cases. And much for the same reason, the query engine that you have is not necessarily optimized for this kind of thing. It bogs down, that kind of stuff. You want to have a database that's geared towards these hot applications. And these serving databases, one of them is Druid. Surprise. There's others that people use. So some of the first products used in this slot in the big data world, I would say HBase and Cassandra were some of the first ones used here. Druid is one of the ones used today. There's a ton of others used today. What tends to categorize these is they are databases that are storing a copy of your data in a way that's optimized for some particular kind of query workflow, as opposed to a query engine that is querying things out of the data lake on demand. Okay, so that being said, let's talk a little bit about Apache Druid now that we've sort of contextualized it in the world of the big data space and what's going on. Okay, so Apache Druid. Druid powers analytic applications, like I mentioned. That's its purpose. Its purpose is not necessarily do everything you can think of. Its purpose is to power analytical apps and do it very quickly. So, example on the left, we have imply pivot, like I was mentioning earlier. There's also connectors from stuff like Looker, Metabase, and Superset into Druid, and Druid speaks SQL, so you can write your own applications. It's used in the wild. It's pretty popular in Silicon Valley amongst all these folks that have tons and tons of data for, I think, a good reason, because when you have the scale of data, then getting super high performance analytical applications does demand solutions like Druid, does demand technologies like Druid that are able to deliver that on really almost any imaginable scale of data. So a few snippets here of blogs that you can look up online if you're interested, from Netflix, from Twitter, and from Airbnb about how they use Druid. Some numbers from out there in the world of Druid in the wild. People are loading 100+ billion rows per day, the Druid clusters, retaining trillions of rows over a year of data in a single cluster. Single clusters with hundreds of servers. Actually, I think that there's a few people with thousands of servers now. And all this with sub-second to a few seconds of query latency, and a mix of streaming and batch ingest. So I guess my point is that even at these scales, you can still support sub-second to a couple seconds query latency on this huge amount of data. And for most of the rest of the talk, I'm going to talk about how this works, and then connect it back into thinking about what makes systems like Druid that you can think of as a database different from systems that are like query engines that you can think of as querying data out of a storage system, out of a disconnected storage system. So before that, a little bit of motivation as to why you might care. Druid is designed for performance. That is its purpose. And here's a independent benchmark done a couple years back, not by anybody affiliated with the Druid project, which is the best kind of benchmark. Independent benchmark showing Druid performance versus Hive versus Presto. I would say two good examples of query engines that are designed to query things out of a lake. And you can see here that Presto is a bit faster than Hive. It's a bit newer generation, which shows up in the speed. But also both of these are orders of magnitude slower than Druid, and that is why that's I guess my motivation for you as to why you should care about this kind of stuff. Okay. How does it work? Hopefully, I've motivated you enough to be interested in listening to a bit about how it works under the hood, which is the part that as a technologist I find the most interesting. So Druid uses a microservice architecture. I'm not going to get into the details of it. I just want to talk really high level, just so we have the right vocabulary to talk about how the system or what's happening in the system. So the vocabulary here is we have servers. There's 3 server types in Druid: query, data, and master server. The master server is about coordination. It doesn't actually touch any data. It's all about metadata. The query server is stateless. It does touch data, but it doesn't have any state. It doesn't store data long term. It's only involved in querying data for specific queries. And the data servers are the ones with all the long-term data storage. So what happens as data comes into them, it's either in streaming or in batch. We have these processes called indexers that read data and then write what we call segments here. I know I'm throwing a lot of terms quickly, but if you take away one thing from this slide, take away the fact that there are these segments, these little files that are getting pushed in and out of deep storage. These are like little slices of a table. Each one is a few million rows. And this is sort of the unit of computation in the system. As data comes in, we create segments out of it. And as you query data, we collect all the segments that relate to the table that you're querying. Each table might be thousands of segments. And then we query all those segments individually and then merge the results. And that's the core concept here. The query engine and data format are tightly integrated. So the segment format uses some of these techniques that I'm going to get into. One is compression. Of course, compression is great. Secondary indexes. This is the idea that we have a primary index on partitioning. So that's something that's really common to pretty much any system that's querying big data. You're going to partition it in some way. generally on time or user ID or something like that. And then if you have a filter on, let's say, a partition on time, if you filter on time, then we will know which partitions correspond to that query, and we only have to query those partitions. And this is something that almost every system that interacts with big data implements, because it's such a meaningful optimization. Structure organize the data by time, and pull out the specific time ranges that match a query. In Druid, we go one step further and we do secondary indexes. So we don't just have the primary partition index, we also have the secondary index on every column. Operating on compressed data, that's really important. So don't decode data until you need to. And then late materialization, that's just a fancy database person term for not reading things that you don't have to read. And I'm going to go through an example in a little bit about how a query is run to sort of see how these things interact. So here is a example segment. And this is a segment that has 8 rows. And you can tell it has 8 rows because the time section here has 8 rows in it. The artist section here has 8 rows in the data section, and there's 8 prices and 8 counts. This is sort of I guess, a pre-pandemic data set about ticket sales. So what we have is we have artists selling tickets in various cities at various times and for various prices and various numbers of tickets. So what might we want to know about this? We might want to know all the cities that AC/DC sold tickets in, and the total ticket price of each for each city. So select city, sum of price, group by city, where artist equals AC/DC. And so I'm going to go through an example of how this is computed, and hopefully that gives a flavor of how the engine and data format are integrated, and how this sort of speed is achieved. So the first thing we're going to do is we are going to resolve the filter. So we're going to resolve the filter artist equals AC/DC. And the way that we're going to do this is on the data servers, all of these segments are prefetched. They're all memory mapped. So we can random access through them. As we run, they're not necessarily all stored in memory, but they are memory mapped, meaning that if the system has memory to store the chunks you're reading, those chunks will all be cached in memory. And if you have enough memory to cache everything, it'll all be cached. And if you don't have enough memory to cache everything, it'll cache what's been used recently or frequently or that kind of thing. So one really important technique is to split the segment up into these sections and only read the sections that we have to read, because that puts less pressure on the cache. If we never read a certain section, we don't have to load that in memory. So it means we don't need to have everything 100% memory, and we can still random access through it. So what we're doing first is we're going to read the dictionary section of the artist column. The values in every dictionary are stored in alphabetical order. So we can do a binary search through the dictionary in order to find the row for a particular value. We don't have to scan linearly. It doesn't really matter here for this 3-element dictionary, but if there was 10,000 elements, it would be a nice optimization there. So here what we do is we do that binary search. We find the AC/DC is 0. So we know it's number 0. Then what we're going to do with that is we're going to read the 0th, the first entry, out of the index. The index and the dictionary match in terms of ordering. So there's 3 of each one. The first index entry matches the first dictionary entry. So it says 0, 1, 2 here. And that means we know that AC/DC appears in rows 0, 1, 2. Now, a brief note here, there's 2 kinds of compression being used. One is dictionary encoding, which is a sort of kind of compression. So we're not actually storing each string value in every row. We give each one a dictionary code, and you see the data section just has 1s and 0s, 0s and 1s and 2s. So it has those dictionary codes, not the strings. And so we're compressing that way. And then the indexes are stored as bitmaps. So the 0, 1, 2, we don't actually store an array of 0, 1, 2. We store a bitmap where bits 0, 1, and 2 are set, and then we compress that with a technique called roaring bitmap compression. So the index is actually quite small. Okay, so we pull the bitmap and we see from the compressed bitmap that 0, 1, and 2 are the rows that match this particular filter. So now we're done with the artist column. We're actually not going to look at the data section, which is great. It means we don't have to read it into memory. We don't have to transfer it to the CPU. So we're kind of minimizing what work we're doing. Then we go to the city and price columns. We look at the first 3 of each because we know we matched 0, 1, and 2 as row numbers. So that's the first 3 rows. We look at the first 3 rows of each. We then aggregate those. So we say like 1 is 2912, and then 2 has 1800 plus 1953. So we build a little 2-element aggregation in memory. Then we go to the dictionary, and we saw 1 and 2 in the data section. And so we're going to look up 1 and 2 in the dictionary. We're not going to look up 0 because we didn't see it, so we don't have to look it up. And then at that point, we are done with the aggregation. We're done with the aggregation. And the nice thing is we have looked at very little here in this segment. We did not look at the data section of the artist column. We didn't look at anything in the time column because we didn't need to here. We did a binary search in 1 dictionary. We did a random access in 1 index. We did a couple random accesses in another index for city. And then we read 3 values out of the data section for city and price. And so we're being very economical with what we're reading. And this is taking advantage of the fact that we're not actually reading this data file over a network. We have prefetched it. And so because we prefetched it, we have it indexed, we can scan through it, we can cache it in memory. And this is really the key to how we achieve high performance in the system. Okay, so the last thing I want to talk about is can we have it all? So can we imagine, it's annoying to have different systems for different things because, I mentioned that these systems designed for hot analytics tend to not be as powerful on the query side as systems designed for colder stuff. And they also tend to be more expensive for infrequently accessed data. On the flip side, the colder systems tend to be more expensive for frequently accessed data, and they tend to have worse performance, a higher performance floor. So, it tends to mean that, there's no, a system like a query engine, like I don't want to pick on any one, but a system like Hive or Presto, you're never going to scale it out enough to get queries down to 10 milliseconds, but you will be able to do that with Druid. So the performance floor is lower, but can we have it all? Can we imagine these systems getting closer together? So let's think about that. Let's look at what's different between them. So if you think back to this picture here, where you have Druid reading from a data lake and a query engine reading from a data lake, for the query engines, data is fetched on demand. For Druid, it's fetched ahead of time and it's partitioned and indexed. So that's a major difference. And what's similar between them? What's similar is they're both elastic. So with Druid, we can scale nodes, we can scale out, we can scale in. They're both fault tolerant. They're both shared nothing. So they have these things in common. I think they actually have a lot more in common than they have different. This big difference is, are we fetching data on demand or ahead of time? And have we optimized for one or the other? Some other differences: query engines support federated data sources and spot elasticity. And by that, I mean you can increase the size of a cluster and be able to use those new servers almost immediately for a query. Whereas on the Druid side, or generally anything that's storing a copy like Druid does, any similar system, there's going to be some period of time when you scale up where data is rebalancing. And in Druid's case, that's automatic. You don't have to do anything to make it happen, but it does take time. And so if it takes about an hour, that means when you scale up, it takes about an hour to be able to leverage those new nodes. And before then, you're just, they're not being fully utilized. And so the spot elasticity is not there. So on the Druid side or on the hot side, you're going to get better performance on the same hardware, lower performance floor. So you'll have for situations where you do have very frequent access and you are going to have a cluster running very often, these are better choices. So the last thought that I want to leave with is going back to this picture of how Druid works, calling back to that diagram from earlier. You know, we have indexers reading data, pushing segments to deep storage, and then the historicals pull them from deep storage, prefetch them, and then memory map them, and are able to sort of skip around using the indexes, using the dictionaries, skip around to be super economical and very low cost for this frequently accessed stuff. You know, you can imagine a world where we don't prefetch. You can imagine a world where you have a system like Druid that decides, you know what, I'm going to forego using the indexes. I'm going to forego doing it that way. I'm going to scan things more front to back, do it in a way that might be a little less economical. And so I'm going to sacrifice some performance. But what I'm going to gain is I'm going to gain this on-demand elasticity, the spot elasticity stuff, being able to query data over the network, which enables new servers to be used to be leveraged immediately. And you can kind of imagine that. And you know, I think that these systems are maybe not as far apart as it may seem that they are. And that's one of the reasons that I find it so interesting and exciting to work in this space. There's always new things happening. So with that, I will leave you and thank you. And any questions?
Thank you very much, Gian. Yeah, I would echo that. If there's questions for the folks that are here, either in the chat or in the Room C Slack channel, I can feed those to Gian. We have one from Scott Nickel. What are the metrics regarding data loading?
I guess, do you mean like how much data the system can load per second, or that kind of thing?
What, you want to start?
Well, I'll answer it that way. If that's not what you meant, then you can correct me. So I mentioned that the system supports batch and streaming ingestion. Batch ingestion, pretty much the sky is the limit. You know, you can scale out to as many indexers as you want, and then load as much data as you want. It's limited mostly by your own imagination and by how much disk space you have on the Druid servers. On the streaming ingestion side, there is some coordination involved, so it may not. There may be a limit that is lower than your own imagination. The most I've seen someone load per second into a single table is somewhere in the tens of millions of records per second. Nothing really bad was happening then, so I think it would keep working beyond that. I think it's at some point you'd probably run into some kind of limitation, but certainly tens of millions, approaching 100 million per second into a single table is something that I've seen happen.
All right, thank you for that. If there's any other questions? And I guess I would encourage also if there's follow-up questions after we finish the presentation, to continue to post them into the Room C Slack channel. I'll get you an invitation for that, Gian, if you don't have it. And maybe there can be some discussion after the session is over. All right, we have another question. Does Druid keep data in memory or on disk?
Yes, both. So it keeps it on disk and it memory maps it. And because we are all good programmers, there's a really nice article, a really nice essay out there. I think it's from one of the people associated with Perl that is talking about the virtues of a programmer. And one of them is laziness. And all good programmers are lazy. And because we at the Druid project are lazy, we write the files to disk, and then we memory map them, and then we let the OS decide what's going to be memory and what's not. So we don't implement our own memory caching system, but you know, the page cache in Linux is pretty good, so we just use that. And so Linux will, it's typical on a Druid data server to see the free memory on the server be 0 because the OS is using pretty much all of it for page cache. And so if you have enough memory for the OS to cache everything, then it will basically be an in-memory data store. And if you don't have enough memory, then the pages will go in and out of memory as needed. And the OS will manage that. And that is one of the reasons why, to make sure that process works well and doesn't cause performance issues. That is why we have the data organized the way that we do. That's why we organize it into columns and into sections. And so the idea is that if, in that example I mentioned earlier, we don't read the data section of the artist column. And you could imagine that if you have a lot of queries being issued that don't use a certain column, or if a certain column is infrequently accessed, or if a column is mostly used for filtering, but not for grouping, and so you're going to use the index, but not the data section, then we don't need to load everything in memory. And so we'll still perform as fast as if it was all memory, even if you don't have enough memory. So that's a pretty nice, consequence of how we lay the data out.
Okay, thank you for that. Another question from Scott Nickel. Again, thank you for the questions. Does anything prevent Redshift, Snowflake, et cetera, from incorporating some of the data storage techniques that Druid uses?
Yeah, really good question. Druid's open source, so you can always go read the source and see what it does. So I guess in that sense, no. I would say that for something like, the biggest thing that I think differentiates some of these systems is, especially Snowflake, is Snowflake is kind of a little bit of a hybrid between a query engine and a database. But to my understanding, and it is proprietary, so I guess I can't read the code, but my understanding is that its data format is geared more towards reading over the network than reading locally. And so it doesn't use indexes as aggressively as Druid does. Indexes that involve a lot of random access are something that work best if you have the data locally, where you can cache it in memory and then bounce around through it. So I think that things like that, things like, are you trying to build a system that is geared towards data that's local to the servers, or a system that's geared towards data that's in cold storage and pulling over the network? Which of those things are you building for your users is more likely to constrain what people do than just like ideas or access to source or anything. Because I think that the ideas that all these systems use are pretty open. I mean, it's even though Snowflake's code is private, they've written a lot of papers about what they do, and we've written papers about what Druid does. Google's written papers about what their things do. There's papers written about all this stuff, and there's kind of no shortage of ideas. But people are building systems with different goals, and I think that's the bigger driver of how they operate. I hope that answers your question. That's actually kind of. I'm glad you asked that, because it's kind of the point of the talk. The point of the talk is that it is very difficult to have it all.
Thanks very much. All right, well, I appreciate you joining, Gian. You recovered nicely from the slightly late start, so thanks very much for being here in ETE and giving your presentation. Is there anything you want to say, or last words before we end the session?
No, I think I'm good. Thanks for hosting. Thanks for helping us recover from my tardiness. Appreciate it.
Absolutely, not a problem. And again, let's keep the discussion going in the Room C Slack channel. And thank you all for attending. And we'll see you tomorrow for ETE Day 3. Thanks very much.
Hey, thank you.